Hello everyone. Today we'll be taking a look at properties of arithmetic sequences and series. Okay, so the first property. The common difference can be 0, positive, or negative, right? 0, positive, or negative, right? This is, I think, one of the most obvious properties. I really don't need to go into detail about this, but I'll just give you guys a few examples. So we can have an example as 1, 3, 5, 7, and so forth, where here the common difference is plus 2. Then we can have another sequence where we have 3, 0, minus 3, minus 6, so forth, where our common difference is minus 3. And we can also have another sequence, right? Here we can have 7, 7, 7, and 7, right? Here, the common difference is 0, right? So I just put in this property, even though it's completely unnecessary to put in here, just because I know these are quite obvious, right? But oftentimes students get confused about this. So, when they see a sequence which has the same number repeating again, they kind of, think they're like, okay, is this an arithmetic sequence or is it a geometric sequence or what are we looking at here? Or is it just a number repeating? So I just thought, just so there's no more confusion moving forward, I just thought of putting that, mainly because of this. If you have a sequence with the same number repeating, it's an arithmetic sequence, and it's especially an arithmetic sequence because the common difference is 0. All right, let's go move to the next property. Number 2. If A, B, and C are in an arithmetic progression, then 2A is equal to A plus B. All right. So in my opinion, this is a very, very important property, right? You will find a decent number of questions with respect to this property. So let me just explain, let me just derive how we get this. So we have numbers A, B, and C in our arithmetic sequence, right? Now, we know that these numbers are basically they're different because they're being added or subtracted by a common difference, right? So either we can just put plus d and plus d, and then we can make d is equal to some real number, right? Some real number at this point. Okay, so now, so this can be also be written as a plus d, a plus 2d, right? Just another way of writing it. It's the same thing, right? It means absolutely the same thing. Now, we know that the common difference in this case will be b minus a, or common difference will be c minus b, right? Now, if we equate equation 1 and equation 2, what we get is b minus a is equal to c minus b, right? Again, now if we bring the letter b's to the left hand side, we get 2b is equal to a plus c, right? This is how we derive it. It's a fairly simple one, and it's actually quite important. So you really don't need to memorize it. Even if you know how to derive this, it's more important to know how to do that, because when you're in an exam, the pressure and the time and everything can make you confused. You can be confused with certain things, and this is why I just wanted to show you how we come to this entire property. So again, just to reiterate, basically, whenever we have a number of 3 sequences, the middle term, when you multiply it by 2, and you just add the first and the last term of the sequence right here, first and the last. So, or I can just say first and the third, to be honest. I don't want to say last because that might throw some of you guys off. So, second term multiplied by twice, multiplied by 2 is equal to sum of the first and the third term. All right, let's look at a question regarding this property. So we have if log base 3 2, if log base 3 2x minus 5, and log base 3 2x minus 7 by 2 are in an arithmetic sequence, determine the value of x, right? So we have 3 sequences right here, right? Log base 3 is 2. We have log base 3 is equal to 2x minus 5, and log base 3 2x minus 7 by 2, right? So we know this is our, let me put in another color. We have our A, we have our B, and we have our C, right? So if we use the same property that we have, right? We use 2b is equal to a plus c. What we get is 2, we get 2 log base 3, 2x minus 5 is equal to log base 3 to 2 plus log base 3 into 2x minus 7 by 2, right? This is what we get. So let's simplify this a bit more. Well, we know if you know the log rules, we can just put this up here. So what I'm going to do is I'm going to do log base 3, 2x minus 5 whole square. And then I'm going to group these two together. So we get 2 into 2x minus 7 by 2, right? I'm going to simplify this a little bit more. So we get log base 3, 2x minus 5, 2, squared is equal to log base 3 into 2 into 2x. Now I'm not going to do 2 raised to the power x plus 1, and I'll tell you that why. I'll tell you about it why just in a bit. So I'm going to do this. And now let's go to the next slide. So we had log base 3 2x minus 5 whole square is equal to log base 3 2 times 2 to the power x minus 7, right? Now we can cancel the logs from both sides. So we're left with 2x to the power 5. Sorry, 2x minus 2 to the power x minus 5 whole square is equal to 2 times 2 to the power x minus 7, right? Let me just rewrite this properly so there's no confusion. Okay, now what I'm going to do here is I'm going to make a substitution. And the substitution that I'll make is t is equal to 2x, 2 to the power x, sorry. Now, if we do that, what do we get is t minus 5 whole square is equal to 2t minus 7. Okay? Now, again, let's evaluate this now. So we get t squared minus 10t plus 25 is equal to 2t minus 7. Let's simplify this a bit more. We get t squared minus 12t plus 32 is equal to 0. Let's make our factors. We get t minus 4 and t minus 8 is equal to 0, right? So now we get t is equal to 4 and t is equal to 8. Now we're getting two values of t, right? No, that's not a problem. Let's find the value of x, okay? So we get 2 raised to the power x, or let me do it in a different color. So we get 2 raised to the power x is equal to 4, x is equal to 2, and 2 to the power x is equal to 8, and x is equal to 3. All right. Now let's look at our original sequence. So we're getting values as x is equal to 2 and x is equal to 3. Or what we can do is we can directly make a substitution because there's already 2 raised to the power x in our entire sequence, right? Here and here. We can just put, instead of 2 to the power x, we can just put 4 and 8 in each case. So if we do that, what we get is, let's make two different cases, right? So let's take blue again. So if we take case 1, where 2 raised to the power x is equal to 4, what we get is log base 3, 2, and then we have here, we get log base, this will be 4, and we get minus 5, so that will be minus 1. So, and this will be 4 minus 7 by 2, which is 0.5. So if we put those things in, we get log base 3, 2, log base 3 minus 1, log base 3, which is half, right? Now, if we take a look at this, right, this is okay, but this is not okay. Why? Because if you look at a log function, right, log base anything can't, this part cannot be a negative number, right? This is a negative number, and if you know about the log function, right, you will know that you can't have a negative thing because nothing raised to the power will give you a negative number. So this entire sequence gets rejected, right? This case will get rejected. Now let's move to the next one. We have case 2, which is 2 raised to the power x is equal to 8, right? So we have, again, log base 3 to the power 2. Not 2 to the power 2. Log base 3, 2. Then we have log 3, and we had was, so we'd put 8 here minus 5, which is 3. So we get 3, and then we get here 8 minus 7 by 2. So I'll just write 8 minus 7 by 2 because I just know it's a positive number. So 8 minus 7 by 2, right? Doesn't even matter. So these are all positive numbers. So I don't even need to worry about it because I know this will be my sequence. I mean, honestly, there's a chance that this could have been my sequence as well, or I could have had both. I honestly don't know. But because this was incorrect, right? Because there was a negative number, I had to, remove this entire sequence. So now I'm left only with this sequence, and that is my final answer. So this is my final answer. Case 2 works, and this is my sequence. So this was how you use the property of 2b is equal to a plus c, right? Like you just saw a question. Again, this was a slightly lengthy question because it had log functions. You can have maybe slightly easier functions as well, but you can have the same difficulty of questions as well. So, it's important that you know your log functions and all that, and it's okay if you don't. I'll be taking a look at it. I'll be explaining it in the functions chapter. So if you were a little bit confused about some properties or what happened, that's okay. We will take a look at it later on. All right, third property. Considering numbers in arithmetic sequence. So what I mean is, suppose we are given any arbitrary, numbers, and they're claimed to be in an arithmetic sequence. Suppose we're given 3 numbers, right? 3 numbers. So how we evaluate it is we always take the first term like this. Sorry, the middle term of the 3 numbers is a, right? And then we take a minus d. Sorry, a plus d, and we take a minus d. Okay, if you remember in my first video, we had done a question like this, right? When we were given 3 numbers are in an arithmetic sequence, find the first term and find the common difference. We evaluated something like this, right? So this is how you always operate, right? This is how we always work forward, no matter what question you're given. But if they're asking for, they're asking for the first term and the common difference, and they're given 3 random terms which are claimed to be in an arithmetic sequence, you always apply this process right here, right? This will always, give you the right answer. Okay, so now this was for 3 numbers. Now what would happen if you were given 4 numbers, right? You know how to deal with 3 numbers, but if you're given 4 numbers, how would you exactly, go about it? So in this case, what you do is you take a minus d, a plus d, and you take a plus 3d, and you take a minus 3d. These will be your 4 terms. Because again, if you look at it closely, numbers will cancel out, right? When you add them, all the minus 3d plus 3d minus d plus d, they will all cancel out, right? So this is why we work with such numbers, because they're so convenient, right? You don't have to, work out too much. The math doesn't get a little does math does not get hairy. So it's really easy to work with, simple, straightforward. This is why we use this process. However, one note I want to make is here, the common difference is actually 2D of the sequence. It is not D, right? So suppose you are asked to find 4 numbers, and you're told find the terms and find the common difference, or find the first term, find the common difference. I don't know, right? Just note that whatever value of the common difference that you get here is not the final common difference. The common difference will actually be multiplied by 2, right? So let me denote it like this. D dash is equal to 2 times D, where D dash is not final, I would say, the actual common difference, right? Okay, and suppose if you had 5 numbers, then what would we do? So for 5 numbers, what we do is we take, again, because there, we can have a center number. So we take again a, then we take a plus d, then we take a plus 2d, and here we take a minus d, and here we take a plus 2D, right? It's kind of similar to the pattern with the three numbers, right? You just added a plus 2D here. And, if you had six numbers, you know what you would do. But I doubt they would ever, go that far, because that would just make the question very lengthy. And, you can ask that, examiners can check your conceptual knowledge just by uh, giving you questions with three or four numbers. I don't think five numbers will, that chance will ever, arise in an IB paper. All right, so let's look at a question with respect to this property. So, four numbers are in an arithmetic sequence, right? We have four numbers. Their sum is equal to 20, and the sum of their squares is equal to 180. Find the common difference and of the sequence and the four terms, right? So, we're given four terms. So, if you look at the previous slide again, what I said for four terms is we take this approach, right? For four terms. Let me put this in a different color so it doesn't mix up. Yeah. Okay, so we have this. We'll use this. So we're given a minus 3d. We have a minus d. We have a plus d. And we have a plus 3, right? These are our four numbers, okay, which are in an arithmetic sequence. Now they say the first part is their sum is equal to 20. So let's add them up. So if we add them up, we get a minus 3d plus a minus d plus a plus d plus a plus 3d. Obviously, 3d plus minus 3d plus 3d cancel out, minus d plus d cancels out. So we're left with 4a is equal to, which was 20, right? This is what we're left with. So a is equal to 5, right? This is first part. We've already found a. Now we have to find the common difference, right? Or sorry, not the common difference, the d, right? Remember, the common difference d dash is actually equal to 2 times d. Remember that. Don't mix that up. So now the second part says the sum of their squares are equal to 180, right? So what that means is a minus 3d whole square plus a minus d whole square plus a plus d whole square plus a plus 3d whole square is equal to 180. All right, let's evaluate this on the next slide. So let me just rewrite it really quickly. So let's evaluating this, what we get is a square plus 9d square plus minus 680 plus a square plus d square minus 280 plus a square plus d square plus 280 plus a square plus 9d square 680 is equal to 180. Okay, so this will cancel out with this will cancel out with this, and what we're left is we have 1, 2, 3, 4 a squares. So we have 4a squares. Then we have 9, 10d square, 11d square, and 20d square. So we have 20d square is equal to 180. Now if we divide by 4, what we left with is a square plus 5d square is equal to 45. Right? We know a is equal to 5, right? Which we found out from the previous thing. So let's, substitute it back in. What we get is 25 plus 5d squared is equal to 45. 5d squared is equal to 20. D squared is equal to 4. And d is equal to plus or minus 2. Right? So let me move this. Let me just put this here so we have a little space. Okay? Now. All right. So now we have D and we have A, right? So now what we need to do is we need to find the common difference and the four terms. So let's find the common difference later. Let's find the first four terms, because then we just need any two terms and we just need to subtract them and we'll find the common difference, right? So Let's do a plus d, a minus d. So we get 5 plus 2, and so we can take actually any value of d here. We can take plus 2 or minus 2. We'll actually get the same answer, and you can try that on your own later. I'll just take plus 2 because it's easy to work with. So we would have 5 plus 2, which is 7. 5 minus 2, uh, which is 3, and then we would have 11, and we would have minus 1. Right? These are our four terms of the arithmetic sequence. So now, if you take a look closely, our common difference is 4, right? Because if we do 7 minus 3, we're getting this 4 right here, right? So it was not 2, right? Like I said before, like I mentioned it here, our d dash, which is our actual common difference, is actually 2 times the value of d, right? We could have just multiplied by 2 and then just said, okay, d is 4. But I just wanted to show you guys, what it really means. So yeah, this was how you use property number 3. All right, property number 4, and I think this is an important property as well. So what it says is, if each term of an arithmetic progression is increased, decreased, multiplied, or divided by the same non-zero number, then the resulting sequence is also an arithmetic progression, right? So suppose we have a sequence, right? Let's say we have a plus d, a plus, or not even like that. Let me just put it like a, b, c, right? We have these three numbers are in an arithmetic sequence. So now if I multiply some constant, right? So if I add or subtract some constant for on all of these terms, right? This will remain in an arithmetic sequence, right? This is an arithmetic sequence or an arithmetic progression. It's the same thing, doesn't matter. This will also remain in an arithmetic progression, right? So if I had 2, 4, 6, for example, and I added 1 to all of them, then we would have 3, 5, 7. That will still remain an arithmetic progression, and the common difference, and that will be same because the common difference is still the same, right? Now let's take it a step forward. If I multiply or divide, right? So if I okay, you know what, let me change this and let me put in some other value. Let me put in x, for example. mm, x and x. Okay, and suppose now, if I would take it a step forward, I would put, maybe, I don't know, let's put m by n, a plus or minus x, m by n, b plus or minus x, m by n, b plus or minus x. This will also remain in an arithmetic sequence, right? So again, if I had 2, 4, 6, and I divided it by 2, what would I have? 1, 2, 3. That is still an arithmetic sequence because the common difference exists and it's 1, right? So this is an important property in my opinion. And again, it's nothing, too crazy. You can just be aware of it. If I add any, subtract any constants, the whole sequence is still, an arithmetic sequence. If I multiply or divide by some constant, it's still an arithmetic sequence. Okay, so let's take a look at a question. If b plus c minus a upon a, then we have c plus a minus b upon b, a plus b minus c upon c are in an arithmetic progression, then show that 1 upon a, 1 upon b, and 1 upon c are also in an arithmetic progression. So I highly recommend that you pause the video and try this question on your own, right? This is a really, out of the box question. And without knowing this property, you would have never been able to, even, think about what to do. But now that I've mentioned this property, try to, manipulate something, try to add, subtract, multiply, or divide. Just try to, do some manipulation and try to, get somewhere. And then, if you can't, give it 10 minutes, give it 15 minutes, and then after, resume the video. So assuming that you've given a go at it, let's get started. So we're given, let's take a different color, but we're given b plus c minus a upon a, c plus a minus b upon b, and a plus b minus c upon c, right? Now, in these cases, right, in these types of questions, it's really, really important that you know what your final end product is, right? This is your final end product, okay? You're trying to get 1 upon a plus 1 upon b plus, sorry, not 1 upon a plus 1 upon, just 1 upon a, 1 upon b, and 1 upon c, right? That is your final output. Now, knowing the property that you can add constants, subtract constants, let's try to do something like that. Now, initially we want 1 on the numerator, right? That means we want this entire thing to be removed some way or the other. So what we can do is, to remove it, we need something, we need common numbers on the numerator, right? Right, only then if we divide by the same thing, then we can remove it, and therefore by the property, if the property will hold, and therefore the entire sequence will remain in an arithmetic progression. So to get this, to get the numerator as the same value, what we can do is we can add by 2, right? We can add by 2 everywhere. And if you look closely, what's going to happen is, you see this minus a, minus b, minus c, right? So you see this, whatever variable is minus, that's the same thing on the denominator. Minus b, b, minus c, c. So what this is going to do is, when I add 2, I will be changing this minus c into plus c, minus b into plus b, and minus a into plus a. I'll show you how. So now that I have added 2, what I'm going to do is b plus c minus a upon a plus 2a upon a, right? I multiply and divide by a on both sides so I can get a common denominator. Same thing I'll do here. So I'll get 2b upon b, and I'll get a plus b minus c upon c plus 2c by c. Now I'm going to add them, right? So if I add them, what do I get? Let's go on the next slide. What I'm going to get is a plus b plus c upon a. Then I'm going to get a plus b plus c upon b. And then I'll be getting a plus b plus c upon c. So now if you notice that our numerator is the same, right? A plus b plus c, a plus b plus c, a plus b plus c, right? So we added a constant here, right? Let me put this in yellow. We added a constant, right? And according to the property, that's okay, because the whole sequence is still in an arithmetic progression, right? It's still an arithmetic sequence, right? This is still an arithmetic sequence, right? So it's all good, right? We're still doing it fine. Now, if you notice, we want 1 upon a plus 1 upon b plus 1 upon c. So how simple is that? We just need to divide. If we just divide, let me rewrite this. We just have to divide by a plus b plus c, right? And we'll get 1 upon a, 1 upon, 1 upon b, and 1 upon c, which is the desired end product, right? That's what we wanted to show. And because we just divided by some constant values, right? A plus b plus c, some constant value, and we're doing that for every single term here. So that doesn't matter, because our thing will still be in an arithmetic sequence. So it's good. We're perfect. We have proved it, and we haven't changed anything, because we have used the properties that were mentioned here, right? So this was the last question of this chapter, or I would say the properties of arithmetic sequences and series. And I think this is all there is for arithmetic sequences and series. And in the next video, we'll be taking a look at geometric sequences, and then after geometric series, and same thing, properties of geometric sequences and series. And probably another 3 to 4 more videos, and that will wrap up the entire sequences and series for the IB math. And maybe I might make an additional video where I'll take a few out of the box concepts which will be applicable in paper 3, right? Because paper 3 is this is a portion where you get something out of the box, and you're expected to understand the concept there, and then apply it also within that 1 hour. So maybe I might take a look at subspecial series and how to approach them if they ever come. But I'll take a look at that later. But for now, yeah, this is all there is, and I'll see you in the next one. Bye bye.